In this video, I'm going to talk about signal flow graphs. How do you find a transfer function from a signal flow graph? What is a signal flow graph? It is a pictorial representation of a simultaneous equations describing a system. So it's similar to the block diagram, what we did in the previous videos, finding transfer function from the block diagram. Similar way, it's almost same, but it looks a little bit different. Let me show you the diagram of a signal flow graph. So here is a signal flow graph, a pictorial diagram. So here you can see R as an input, C as an output. In this diagram, in the signal flow graph, we're going to find the transfer function, find C over R equal to how much. That's what we're going to find in this diagram. Now I'm going to go over some of the basic definitions. So the first one is input node. Input node or source is nothing but it's node with only one outgoing branch. So input node doesn't have any incoming branches, but it has only outgoing branch. So if you look at the picture, signal flow graph here, the input node is nothing but a point where one or two or more elements connected. So here, this is the input node where only outgoing branch is there. This is the outgoing branch. This is outgoing branch. So that's called input node. Same way, output node or sink. A sink is nothing but where it has only, so if you look at here, see output node, it has only incoming branches. There are no outgoing branches. That's called the sink. The next definition is path. It is a continuous unidirectional path of or branches along with no node is passing more than once. So path is a continuous unidirectional succession of branches along with no node is passing more than once. The next definition is forward path. Forward path. It is a path from input node to output node. So it is a path from input node to the output node. Feedback path. It is a path with originates and terminates on the same node. So let me show you both forward path and feedback path. So here in this diagram, the forward paths are, so starting from input reaching to the output. So if I go through 1, Z1, Z4, Z2, 1 and 1, that's one forward path. Another forward path is 1, Z1, Z4, Z3 and reach. So here, starting from R or input reaching output C is called forward path. So in this diagram or in this flow graph, we have two forward paths. Okay, and the feedback path is starting node and ending node is same. So here, if I start from here, this is one feedback path. Okay, and another feedback path. So starting node and ending node, both of them are same. So there are in this diagram we have two feedback paths and two forward paths. Next one is self loop. It is a feedback loop consisting of a single branch. A self loop is nothing but, say for example, here is one path, another. Okay, here is another forward path, another forward path. So a self loop is nothing but it's going to start from the same node, end at the same node. So this is nothing but self loop. Okay, only one branch. Gain. The gain of a branch is the transmission function of the branch. Path gain. It is the product of the branch gains encountered in traveling through a path. Loop gain. It is a product of branch gains of the loop. So these definitions are important when we are solving an example. So you will understand better when I'm solving an example. So we're going to solve this by using Mason's gain formula. It is useful to find the transfer function of a system, which is nothing but the overall gain of the system. So the overall gain is nothing but output over input. The output could be voltage, current, input could be voltage or current, or some other values like force, acceleration, blah blah blah. So according to Mason's gain formula, so the transfer function is defined as 1 over delta sum of p of k delta of k, where k is path gain of, kth forward path. How many forward paths are there? So if there are 3 forward paths, k equal to 3. If 10 forward path, k equal to 10. Okay. Pk is the path gain of kth forward path. Okay, what is pk? We're going to solve an example, so don't worry at this point if you don't understand this. Delta is the determinant of a graph that is defined as 1 minus sum of all individual loop gains plus sum of gain products of all possible combinations of two non-touching loops minus sum of gain products of all possible combinations of three non-touching loops plus etc etc. It looks like a little difficult, but when we are solving examples, you will understand a lot better. So don't worry too much about this. I'm going to solve at least 3-4 examples, so you should be okay. So the transfer function, the important thing is you need to remember this formula. Transfer function equal to 1 over delta equal to, 1 over delta times sum of p of k and delta of k, where k indicates the number of paths. Okay, so I will start with this example. So here is the first example. So in this example, there are first find forward paths. So we're going to use the Mason's gain formula to find out the transfer function. So what is the Mason's gain formula? 1 over delta sum of p of k and delta of k. So p is nothing but the path gain of kth forward path. So in this example, first find how many forward paths are there. A forward path is nothing but you have to start from starting point, input, reach the output without going through any branch more than once. Okay, so here I found 2 forward paths. The first forward path is so here going straight 1 g1 g2 1 g1 g4 g2 1 and 1. So that's the forward path 1. So this is path gain. Okay, this is path gain. What is the path gain? 1 times g1 g4 times g2 times 1 times 1. So z1 z2 z4, that's the path gain. Another forward path you can see starting from R reaching C. So here I'm going through 1 g1 g4 g3 1 and 1. So that is another forward path. We have only 2 forward paths here. So here k equal to 2 basically. Now we'll find number of loops. Loop is nothing but starting point and ending point must be same. Okay, so loop 1 you can see so starting from here, this node right there, g1 g4 h1, that's a loop 1, g1 g4 h1, and loop 2 g1 g4 g2 and minus h2, that's loop 2. Any other loops? Yes, here loop 3 I can go from here g1 g4 g3 and minus h2. Okay, so there are 3 loops, L1 L2 L3. I think in the same video at the starting I said there are 2 loops, but yeah, if you look into the problem a little deeper, we'll find there are 3 loops in this. Okay, and the third important point is find out how many non-touching loops are there. So non-touching is nothing but even they shouldn't touch any path, they shouldn't touch any node. Okay, so here, say for example, here is something. Okay, so here is a 2 feedback loops. Okay, this is g1 h1 z2 h2. So there are 2 loops basically. This g1 h1 is one loop and z2 h2 is another loop. Are they touching to each other? Yes, they have a common node, so they're touching to each other. So how do you define they're not touching? First thing, they shouldn't have any common element. So if you look at L1 L2 L3, g1 is common. Okay, so definitely they're touching to each other. Even if we do not have any common element, still find out here. So in this another example, say L1 equal to G1H1 and L2 equal to Z2H2. Are they non-touching? Even though they don't have any common element in this, but still they're touching to each other at this node. So other than that, they both are so even this flow diagram doesn't have any non-touching loops. They're touching to each other. Okay, so here there are no non-touching loops. Why do you need non-touching loops? Because to find delta, to find delta we need non-touching loops. So if you look at the definition here, sum of gain products of all possible combinations of 2 non-touching loops, 3 non-touching loops, 4 non-touching loops, 5 non-touching loops. So we need to have those. So here we don't have any non-touching loops, so delta is going to end right there, 1 minus sum of all individual loop gains. That's it. The remaining part is we don't need to worry. So all we need is this. So this is going to be 0. Okay, so coming back to our original example, here is the example. So delta equal to 1 minus L1 plus L2 plus L3. Now say for example there are 2 non-touching loops. So L2, L3 are non-touching, so you will end up with for example, okay, in this case it's not true. If say for example L2 or L3 are non-touching loops, then you can say L2 times L3 plus. Okay, we'll talk about it when we go to the next example. And now the transfer function, so the transfer function equal to, so here Mason's formula is transfer function T equal to C over R equal to 1 over delta. So 1 over delta sum of k number of paths, forward path, pk delta k, that's what it is, right? So k here I have 2, so t equal to p1 delta 1 plus p2 delta 2 over delta. Okay, so what is delta 1 is 1, delta 2 equal to 1. How did I find that? So here is the definition. Delta 1 I found cofactor of the kth forward path, determinant of the graph with the loops touching the kth forward path removed. This delta k in this case, so here delta 1 is defined, delta 1 and delta 2 are going to define, here is the definition, let me go through it. So cofactor of the kth forward path, determinant of the graph with the loops touching the kth forward path. So find out, are there any loops touching to the forward path? So here say this is the forward path 1. So I'm going to find delta 1 from this. Is this loop, so here we have 3 loops. Is this loop touching that forward path? Yes. So eliminate that. Is this loop touching that forward path? Yes. Is this loop touching that forward path? Yes. So we'll eliminate those forward paths from delta. So you found the delta, this is my delta, total delta. Okay, so from delta I found delta 1 is nothing but 1. Eliminate all those elements which are touching the forward path. Okay, eliminate all the elements. So for example here G1, G2, G4, H2. The Z1, Z2, Z4 already involved with the forward path 1. So eliminate that. Z1, Z3, eliminate that because this element is involved in this. In the forward path, same thing, G1 is there, Z1 is already in that forward path, Z1, Z2 are right there, that's my forward path. So wherever I see Z1, Z4 or Z2, eliminate that element from the delta. That's how I found delta 1. Same thing I found delta 2. If you do not understand at this point, don't worry, we're going to solve more examples in the future videos. Okay, so the transfer function T equal to C over R P1 delta 1 plus P2 delta 2 over delta. So P1 is, we just found P1, P2, and delta 1, delta 2 over delta. This is our transfer function. I'll stop this video here. I will solve more examples in the next video. Thank you.